Hi, my name is Dawa Thendup Bhutia, BSc Third Sem, and my topic for today is atomic force microscopy. A brief about atomic force microscopy. Atomic force microscopy is a type of scanning probe microscopy which demonstrates the sample in a fraction of a nanometer, which is 1000 times better than the optical diffraction limit. The information that is gathered by using the atomic force microscope is by feeling or touching the sample surface with a mechanical probe. The AMF can be used to image the topography of a soft biological materials, which means the image formed by using the AFM is in the form of a topography or a 3D image. So we need to measure the vertical resolution as well as the lateral resolution for it, and the limitations of the atomic force microscopy is the need for the nanoparticles or the sample to be absorbed into the supporting surfaces such as mica or silica wafers. The absorption of liposomes onto a solid substrate has the potential to modify the size and shape of the vesicle and cause their flattening. So this is one of the limitation of the AFM. So let us look at some of the images of AFM. So the image on the left side is a image of an AFM, and on the right side you can see the setup of an AFM. So this device out here, this is the AFM, which is connected to a computer device or any electronic device, which gives us the image of the sample surface. So by following the process of AFM, whatever data we get is being transferred to the electronic device, and in that electronic device we get to see the um, topographic image or the 3D image of the sample surface. So on the right hand side we have the setup, and on the left hand side we have a simple AFM, and an AFM cost is very expensive. The cost of an AFM is very expensive. So now we have a diagram of AFM. So this is just a simple diagram of AFM, and the components of this AFM are as follows. So first we need a sample, then we have a laser source, a cantilever, a photodiode, a detection and feedback electronics, and a piezoelectric scanner. So from this laser source we get an incident ray, we get this incident laser, which is which gets directly with which hits directly to the cantilever, and from this cantilever we get a reflected laser which is being collected by a photodiode. Photodiode is nothing but a device which indicates the presence of a light. So this photodiode collects the reflected laser, and the data or the current is being transferred to the detection and feedback electronics, which in turn gives the topographic image of the object, or the 3D image of the object. And this piezoelectric scanner is nothing but a paper which does not allow the sample to fluctuate or vibrate. So in simple terms, it keeps the sample in a steady form or in a straight form. So now we are going to discuss about the theory of AFM, and while doing so we are going to discuss about its composition, principle and working. So AFM was discovered by three IBM scientists, George Binning, um, and Christoph Gerber and Calvin Quet of Stanford University. So these three scientists discovered the AFM, or atomic force microscopy. So the main reason for the discovery of this atomic force microscope was to overcome a basic drawback which they were facing with STM, or scanning Turning microscope. That is, the scanning Turning microscope can only conduct image of conducting or semiconducting surfaces. So it formed the images of only conducting or semiconducting surfaces. So the AFM was discovered, and whereas the AFM has the advantages of imaging almost any types of surface, including polymers, ceramic, ceramic, composites, and glass and biological samples. So the main reason for the discovery of this AFM was to overcome a basic drawback with scanning Turning microscope, which is it can only form the image of conducting or semiconducting surfaces. So this was the main reason for the discovery of this microscope. Now, when we look at the definition of atomic force microscopy, it states that atomic force microscopy is a type of scanning probe microscopy which demonstrated resolution on the order of a fraction of a nanometer, more than 1000 times better than the optical diffraction limit. So this is the basic definition of atomic force microscopy, and which simply says that it demonstrates the sample in a fraction of a nanometer, which is more than 1000 times better than the optical diffraction limit. And since the image formed is in a 3D form, we need to measure the vertical resolution as well as the lateral resolution. The vertical resolution is less than 1 nanometer, and when we measure this vertical resolution, we get to measure the depth and or height of the object. We get to measure the depth or height of the object. And when we measure this lateral resolution, we are just measuring the horizontal resolution of the object. So in other terms, we are when we deal with lateral resolution, we are talking about the clarity of the image. We are basically talking about the clarity of the image. The image of this cantilever, when we zoom it in, we get this type of image. So so we know that the cantilever with the tip is being run across the is being moved around the surface of the sample. So the surface of the sample is not a smooth flat region, but it is the surface of the sample has many curved regions and flat regions. So when we move this tip of the tip attached to the cantilever across the sample surface, um, the tip of this cantilever comes across the curved region as well as the flat region. In the first image, in this image A, say A, you can see that the distance between the tip and the flat region is, say, distance d, and the force between them is attraction force, as the distance is long, or the distance is more between these two. But as soon as this tip comes across the curved region, the distance between them gets shorter by x, say x, it gets shorter by x. So now the force between them, the attraction force between them, gets converted into repulsive force. So the we get to see a bending of the cantilever, or the cantilever gets uh, placed a little far, or gets pushed, or gets a different position. So by doing so, the cantilever, the force between the tip and the sample surface changes. So when it comes across the flat region, the distance between them gets increased and we see an attraction force. And when the tip comes in contact with the curved region, the distance gets shorter and it gets converted into repulsive force. So since the position of the cantilever is changing continuously, the incident laser which is falling on the cantilever gets reflected with different intensity and angle, which is being collected by the photodiode. I repeat, where since this movement across the sample surface, the force between the tip changes due to the distance between the tip and the sample surface, the position of the cantilever continuously changes. So the the reflected ray is being the reflected ray of different intensity and angle is being collected in the photodiode. So this is the basic or the working and the working of the atomic force microscopy. This is the working of the atomic force microscopy. And on the left hand side, the simple graph between the interaction force and the attraction force, or the I'm sorry, between the interaction force and the tip position. So from this graph you can see there is a repulsion force and then attraction force, which means when the distance, the can tip, the force between the tip and the sample surface keeps on changing. So hence we get the topographic image or the 3D image on the electronic device or the feedback electronics detector, or the electron, whatever you can say it. So this is the basic principle and working of photo atomic force microscopy. So this is how the topographic image or the 3D image is formed, with vertical displacement and horizontal displacement. So this is the basic working of atomic force microscopy. Now, whatever I explained in the previous slides, these are just the write-up of those stuffs. So you can see AFM by using the concept of solid state physics. The two objects, when they are kept at a farther distance, attraction force is there, and when they come close, repulsive force takes place. You can see when the object are far, they are undergoing attraction. That's the same thing. AFM lies on the electromagnetic force between, relies on this. So this is the concept on which AFM relies, and due to this region AFM also got its name. Then this is the same, while the tip in the cantilever is moved through the sample, it comes across through the curved and flat region, hence gives different intensity and angle laser to the photodiode. The photodiode transfers the data according to the detector or feedback electronics, which gives the topography or the sample of 3D image. So this is the working of a AFM. Now the points to remember for using, when we are using an AFM, we need to remember these points. So first point is select a measurement sample. So we need to check the or measure the sample before reading or using AFM, because a sample, if a sample is not suitable, then it might lead to the damage of tip, sample and piezoelectric scanner. So if the sample is not appropriate, then it might damage the these instruments like the tip and piezoelectric damage. And select and install a probe. So second point, um, probes are made up of different materials in terms of their geometry, cantilever and material. So we need to place a probe of suitable probe for the scanning of the sample surface. And we need to adjust the scan parameter. So we need to adjust the scan parameter correctly, because if we are reading the sample surface at a higher velocity, then it might lead to improper surface tracking and faster tip the tip gets finished faster. So we need to adjust the scan parameter properly. For if the velocity is correct, then the lifespan of the tip gets increased, and we get an improved surface tracking, but at the expense of scan time. But the scan time gets increased, but we might get a proper reading as well as proper surface tracking. And the next one is engage the probe. In some systems, we operator need to manually lower the probe. So we need to manually lower the probe. We need to engage the probe while reading the sample surface. So we need to engage the probe properly. And the fifth point is scan the sample surface. So when we scan the sample surface, the right scan parameter as well as the it is best to observe the progress of the scan. It is best to observe the progress of the scan, because we sometimes need to engage the probe, or select a good sample and select and install a probe. So it is best that you observe the scan, and we need to analyze the scan properly. An experienced AFM user must learn to interpret the AFM image correctly, to understand the tip sample configuration and to distinguish common measurement artifacts. So those are some points to remember for using an AFM. And applications. So AFM generally has three main applications. So the three main applications are or functions are, first of all, as we discussed earlier, it is most commonly used for imaging surface topography by recording the position of the sample relative to the tip, and then recording the height of the probe that corresponds to a constant probe sample interaction, as well as the variety of mechanical, functional, and electrical properties. The basic application of the AFM is that it is used for topographic imaging, and by the use of electromagnetic force between the atoms, we read the sample surface. So that is the basic function. The another function is for surface manipulation using tip force, for example scanning probe lithography. So second function is for surface manipulation using tip force. So this is the second point. And the third point is to measure the force between the sample and the probe as a form of force spectrography, to examine physical and mechanical properties. To examine, so the third property states that we can also measure the force between the sample and the probe. We can measure the force between the sample and the probe, and by doing that we examine the physical and mechanical properties of that samples. So these are the three main applications of the. So now we can see these are the images formed by the AFM. So you can see it helps us in studying the uh, bonding of molecules, and we even get to see the images of atoms, small objects. It helps us to see the bonding, the how the molecules are connected to each other, the type of bonding they are having. So all these images can be seen by using AFM. So this helps us. This has a great value in scientific or studying small nanoparticles or bio, you know, small stuffs, biomolecules and all, the chemical chemistry, biochemistry. This has a very great applications in that too. So the future scope, and the atomic force microscope is widely used in material science. So, as we discussed earlier, atomic force microscope gave us the image of every small particle. So it has a great value in material science, and it also has many application in biological science, since we can see all the smaller stuff. So it has many biological science, but has been limited in use in vision science. The AFM can be used to image topography of soft biological materials. So it can also form the topographic image of biological matter in their native environment, probe the mechanical or properties of extracellular. So AFM has many purposes, as it can see through the cells, atoms, and many biochemical science. It has many applications or uses in biochemical science, and one of the main reason atomic force microscopy has a better future than SPM or other type of microscope is that because it can work in ambient environment. It can work in ambient environment. Moreover, we can also approach this AFM by chemical and electrical methods can also be used for this AFM. So electrical methods, chemical methods can easily be combined on AFM, so it is more easier to use. So the future scope in AFM is better than the STM microscope and all, since it can be used in many purposes. So this so the but however, the complexity of challenges remain open, and the oxidation process of the sample is still complicated. So there are some complications in the AFM which may be solved, or one or few drawbacks of this microscopy may be overcome in the future. So it has a great future scope in science and many other fields. So that's all for my assignment. Thank you.